Hello everyone, this is week 13, first lecture, where we will make some review on matrices and vectors. So first of all, let me remind you that the matrix is a rectangular array of numbers arranged in rows and columns. General notation of matrix is here. Matrix A is, and in brackets we list this array. And in this particular case we have n columns and m rows. So we say that this is m times n matrix. You can notice that the numbers are denoted by a and two indices, sub-indices here. So the first index means that the number of row, and the second index means that the number of column. For example, if we look at element aij, it means that the element in the row I and in the column j. And also we can denote the matrix A as aij, where I is from 1 to m and j is from 1 to n. And also when we don't care about m and n, we just write A, the matrix A is the aij in these square brackets. And depending on the size of the matrix, we have some special matrices. For example, if a matrix has the same number of rows and columns, we call it square matrix. So square matrix is any n times n matrix. Matrix. For example, let's say matrix B is 1, 3, 2, 0. This is 2 times 2 matrix, so this is square matrix. And let's say matrix C is 1, 3, 0, minus 1, 2, 5. It's not square, since this is 2 rows times 3 column matrix. Also, we'll introduce the notion, so this one is square matrix, and if the matrix is n times 1, in this case we'll also have a special name of such matrix. So, and usually we denote such matrices with small letters. So assume that we have, say, 4, 2, 1. This is 3 times 1 matrix. Or we call it vectors. Or sometimes you can see the when we add here the word column vector. Okay, and also depending on the values of the matrix, matrix can be, for example, diagonal. This is a type of matrix where we have non-zero terms only on the main diagonal. Let me show you what the main diagonal is. Assume that we have matrix 4 times 4 matrix. And this thing is the main diagonal. So if the elements of the main diagonal are non-zero and all other terms are zeros, in this case we say that the matrix is diagonal matrix. And also there are some special matrices like for example, zero matrix. This is matrix which consists of all zeros. Let's say this is 0, 3 times 2 matrix. And also the identity matrix, which is only defined for in the case when we have the same number of rows and columns. So the identity matrix is the matrix where you have ones on the main diagonal and all other elements of matrix are zeros. So this is identity. Okay, so we have zero matrix, identity matrix. And also there are some operations which can be introduced for matrices. The first operation is transpose. So transpose is denoted by T. And transpose of the matrix is the same matrix, but now the rows becomes columns and the columns becomes rows. For example, if you want to take transpose, let's say of the matrix 1, 2, 3, minus 1, 0, 4, take transpose, it means that we look at rows and write the row as a column and the second row as a second column. So this is transpose of the matrix A. And also we can introduce the sum of two matrices. So addition operation. A plus B, for two matrices A and B, A plus B is a new matrix, which is if A consists of Aij and B consists of Bij, and if these are of the same size, so these two must be of the same size, then the sum is a new matrix which consists of Aj plus Bij elements. And similarly, we can introduce scalar multiplication. So let's take some number, let's say lambda times matrix A. So this is a number. This is lambda times the matrix, and this is a new matrix which consists of the pointwise multiplication of terms by lambda. Okay, for example, let's look at sum of two matrices. Let's say this plus, and again we must add the same size, the matrix of the same size. So how we add them? We just element-wise, we add them element-wise. 1 plus 2 is 3, 0 plus 1 is 1, minus 1 minus 1 is minus 2, 5 plus 3 is 8, 1 minus 1 is 0, 2 plus 3 is 5. So this is a new matrix, which is addition of these two matrices. Similarly, for example, let's say 2 times a matrix 1, 0, 3, 1. This is a new matrix where we multiply by 2 each entry of this matrix. So this is 2, 0, 6, 2. So here we introduced addition and scalar multiplication. In these two operations, addition and scalar multiplication satisfy the following properties. Let now A, B, and C be three matrices of the same size. Then the addition is commutative operation that we can change order of A and B when we sum them. Also we have associativity for addition. So it means that we can put brackets as we want. Also there is zero matrix, which is zero element of this set. So it means that if we add a zero matrix to any matrix A, we get back to the matrix A. Also for any matrix A, there is inverse matrix, which is minus A. It means that minus 1 times A. And if we add these two matrices, we obtain zero matrix. Also, the distributivity property for scalar multiplication Assume that lambda is some number. If we multiply lambda by sum of two matrices, we obtain that we can open the brackets. So as for numbers, we can open the brackets to get lambda A plus lambda B. Similarly, if we have two numbers, sum of two numbers multiplied by a matrix A, we can open the brackets multiplying A first by lambda and add mu times A. And also, if we have two numbers, again lambda and mu, and if we multiply matrix by mu and then by lambda, this is the same as multiply lambda and mu and then the result multiply by the matrix A, and this is the same as, say, first multiply lambda by A and then multiply the result by mu.